Let's get started. I'm going to talk today a little bit about the Reynolds number, and then I'll go back and talk about other things that have to do with Chapter 4. But let's go over a few questions. If you can get your clickers ready. Okay, so I think I have maybe 4 or 5, I can't remember, but they all have to do with material that we covered in the past couple of lectures. So here's your first question. That's you. Oh, so it was her purse, and she's in this class. We were going to turn it in. Okay, so what is a strict line? Thank you. You're welcome. A, B, or C? Okay, 5, 4, 3, 2, 1, 0. All right, so is it a line tangent to the velocity vector at any point? Or is it a line made up of particles that have previously passed through a common point? Or is it a line describing the actual path of a fluid particle? Oops, that's a mistake. Don't answer again. I won't look at that one. Okay, very good. What? Say that again? Go back? Oh, this is the wrong question? All right. It's still pretty good. So, indeed, it is a line made up of particles that have passed through a common point. That's just the definition of a strict line. The first one describes A is what? Let me close here. A is the definition of a streamline, and C is the definition of path line. All right, so most of you got that right. Okay, if a flow is unsteady, its blank may change with time at a given location. Velocity, temperature, density, or all of the above. This one is easier. So 5, 4, 3, 2, 1, 0. Wow, look at that. So this time the majority is not right. The correct answer is D. All of the above, right? A definition of steadiness or unsteadiness. In a steady flow, the picture that you look at a given time is always the same at any other time. That picture includes everything. Any property or any characteristic of the flow. So it could be velocity, temperature, density, or anything else. In a steady flow, nothing changes in time. Okay, this one is even easier, I think. If a flow is steady, then the streamlines, strict lines, and path lines are identical. True or false? Because it's easier, I'll finish sooner. So 5, 4, 3, 2, 1, 0. Okay, yeah, indeed, it is true. Now, I'm a little disappointed that 53 of you didn't know that. We talked about this last time. So in a steady flow, all these flow lines are the same. In fact, I told you that in a steady flow, when you do an experiment in the lab, the easiest way to do this experiment is to make streak lines, because you can inject something, tracers, at a fixed point in the fluid and see and generate those streak lines. But if the flow is steady, then the streak lines that you're generating are also showing you the streamlines or the path lines, whatever you're interested in. So yes, they are all the same if the flow is steady. Okay, again, a steady or unsteady question. If the flow is steady, there can be a change in velocity at different locations in the flow field, true or false? The flow is steady. Can there be a velocity difference at different locations? Okay, so 3, 2, 1, 0. Indeed, it is true. If the flow is steady, it simply means that at a fixed point that you look at any fixed point that you look at, there are no changes. But if you compare two different places, so at a different location in space, there could be differences in velocity or in any property, in fact. So the answer is A, true. Might be another one. Nope, there are no more. All right, so. Okay, so let's talk a little bit about the Reynolds number. Why isn't this coming on? Oh. And I'm going to think of a simple experiment. Suppose that I have some supply of water. Let's do the experiment with water. Any liquid, in fact, but let's say we're doing it with water. And so we have a supply, a tank, and then we have a long pipe. And let's say that this pipe is clear, so that we can actually see inside the pipe what the flow is doing. So here I cut out a segment of that pipe. Suppose that that's the place where I'm examining what's going on with the flow. And suppose that I ask myself the question, what should be the quantities, the main quantities that affect or that have to do with this? Suppose that I'm trying to find, say, the velocity of the flow. What would affect that velocity? So suppose when I think of velocity here, let's think of some average velocity, because we know the velocity will be different points on the pipe because of the no slip condition. But let's say some average velocity. What do you think will affect this velocity? Tell me something in the experiment that...
The depth of the tank?
Yes, that is true. So let me put that here, because I think... what else? Yeah, suppose that I make it very, very long. But let's list that here too. I could make it very, very long, and I'm looking at a small segment of it so that I don't have to worry about the length. But let's just include it in general. Anything else?
Area. The area. Cross-section.
Okay. What would be a good way to represent, the simplest way to indicate the area? The diameter of the pipe. So let's put the diameter of the pipe. Anything else? Will have an effect on the flow?
Surface smoothness?
That's true. This time I want to leave that one out. Yes, let's suppose this pipe is extremely smooth. so that I don't have to worry about that. But yeah, that could be an effect.
Viscosity.
The viscosity of the fluid. In fact, let me take that back. Suppose that I do want to, here's the smoothness for the person who said the smoothness, but viscosity. What else? Density of the fluid. And perhaps those are enough, but there could be others, depending on how complicated the flow is. So now there is, so if I'm doing an experiment and I want to see what's going on in this flow, I might argue that I have to do a lot of experiments because I would have to change all of these variables to see how they affect the flow. So I could change the fluid and therefore change the density and the viscosity. I could change the diameter of the pipe. I could change the smoothness if we go back to keeping that variable in. The level of the water in the tank, the length of the pipe. I would have to change a lot of things. Now there is a way to reduce the number of variables that you have to examine, and that's called dimensional analysis. And we're not going to look at dimensional analysis today. In fact, you will see dimensional analysis at the very beginning of 130B. But I'll tell you a little bit about what it implies. Essentially, what it means is that you can reduce the number of variables that you have to study if you combine them into groupings that are dimensionless. So, if you form dimensionless groups with these variables, because these variables all have units, right? H, L, and D will have, and epsilon will have units of length. Viscosity will have units of viscosity. Density will have units of density. But if you manage to combine them in a way that you form dimensionless groups, then you reduce the number of variables that you need to examine. I'm just going to look at one combination in particular. Suppose that I want to take my viscosity and I want to combine it with some of the other variables, including the velocity. So anything on that list, what group can I form that I come up with something that has no units? All right. So today we would have to do it by just trial and error. You know, we just try to combine things. When you do formal dimensional analysis, you do it in a formal process and you get the variables that you want. Suppose that I don't ask you about viscosity, but I ask you about any of the other variables. Let's pick, for example, the length of the pipe. How could you make the length, what would you combine the length of the pipe with to make it dimensionless? For example, the diameter. If I take L over D, that's dimensionless. That's easy. Right? Same with epsilon, for example. I could say epsilon, make it dimensionless since it's a length also with the diameter, and so on. But let's focus on the viscosity. What should I combine the viscosity with to make it dimensionless? Remember, the units of viscosity are, anybody remembers?
1/2 second.
Viscosity is not 1/2. That's shear strain rate. Viscosity. Anybody remembers the unit? Yeah, or right. Remember that if you take viscosity and multiply it times the shear strain rate, you get tau. And tau is force per unit area. So you take force per unit area times time, but then decompose the force, you arrive at this. Okay, so what should I combine my viscosity with to make it dimensionless? That means that I have to combine it in such a way that I get rid of the kilograms, the meters, and the second that you see there. How do I get rid of the kilograms? Okay, so what can I do? If I take that viscosity and I divide it by the density, right? Then I got rid of the kilograms. Because now I have kilograms meter second divided by kilogram cubic meter. So the kilograms are gone, right? And in fact, you know what I get, right? I get those units, which are the units of what?
Lux.
No. Which property is mu over rho? Huh? Kinematic viscosity. Right? We saw that already. Kinematic viscosity. But I didn't get rid of everything. I now have meters squared over seconds, so how do I get rid of that? What do I do with a velocity? Let's divide, right? So you say mu, take that that we got first, and now divide also by velocity. That is going to now divide this by meter over second, right? So I'm going to be left with what? A meter. And if I want to get rid of the meter, divide by a length. Since we've been using the diameter before, let's divide by the diameter. So if I take now mu over rho v d, now that has no units. So we did it sort of, it was not quite trial and error, of course, because I knew what to do, but that's the way you would do it if you're just trying to do it by trial and error. So we find that this combination, mu over rho vd, is dimensionless. So the point is that I could just maybe do a series of experiments where I change this quantity rather than changing separately the diameter or the velocity or the density or the viscosity. So for example, what the idea is that maybe if I divide the diameter in half, but at the same time I multiply the velocity by 2, I double the velocity, this quantity doesn't change. And the idea is that maybe the flow characteristics will not change. So in fact, this has a name. And what is the name of this parameter? It's not really the Reynolds number yet. Does anybody know? It turns out that it's inverse. That we define a quantity called the Reynolds number, which was the title of my first page, as the inverse. So the Reynolds number, symbol RE, is precisely the inverse of that. So it's rho v d over mu. And that parameter is perhaps the most important parameter in fluid mechanics. As you advance in your study of fluid mechanics, this course and maybe other courses, you will learn other dimensionless parameters. For example, we looked at some of them up here. The smoothness of a pipe would be described by this parameter epsilon over d. The roughness of the inside of the pipe divided by the diameter, typically a small number. But nothing is as important as the Reynolds number. Why is that? Why is the Reynolds number so important? Because let's go back to the experiment. Suppose that I start out with a very small Reynolds number. Take a look at what the Reynolds number is. Right there. And suppose I start my experiment with a very small Reynolds number. What do you think the flow will look like? Slow is right, because the Reynolds number has a velocity on the numerator. Suppose that I ask you to draw streamlines for that flow, for a small Reynolds number. What are the streamlines going to look like? Suppose I say, draw some streamlines here. Remember, this is a clear tube, so I can see. What do the streamlines look like?
Short.
If they are short, then where's the fluid going? It just moves a little bit and stops? They're not short.
They probably won't turn.
Tell me what they look like. Tell me how to draw them here. Horizontal lines. Right? Nice and simple horizontal lines. Right? Because the fluid is just moving like in layers. Right? And then I increase the Reynolds number a little bit. by, for example, see if you look at the Reynolds number, an easier way to do it would be by changing the velocity. And how could I change the velocity? In the actual experiment. By controlling the height, for example, of the tank, right? So, of the liquid in the tank. Or pressurizing it, for example. So, but if I increase the Reynolds number, I might see that these streamlines look exactly the same. The flow is going faster if I increase the Reynolds number, but the streamlines will look just the same. What happens if I start increasing it more and more and more? What will we see? And so if I ask you to draw the streamlines, you're talking about turbulence. We don't know yet what turbulence is, but you have an idea, right? What happens to the streamlines? Suppose that I crank it up, so I carefully watch those streamlines. I don't want to crank it up all the way that the flow becomes turbulent, but I do it slowly. What do you think will happen if I'm doing this experiment? Now I slowly turn the knob for the Reynolds number up. What will happen at some point? Before it gets what you would call turbulent. Wouldn't you say that, let me draw them with another color, but wouldn't perhaps we see that they maybe start to fluctuate a little bit? That the flow is no longer nice and smooth, but these lines maybe begin to fluctuate or oscillate a little bit as I see them. And if I crank it up all the way, that I get what you call turbulent flow, what do they look like? Wild, right? A mess, right? They might look like that, right? As the flow goes, because the flow now is fully turbulent, right? So in fact, the Reynolds number controls that transition. We are calling this messy flow turbulent flow. What do we call the other one where the lines are nice and smooth and horizontal? Huh? Laminar flow, right? So we can in fact say that there is, here's a different page here, that there is what we might call a critical Reynolds number, some value of it, some value of the Reynolds number, such that if I am below that value, the flow is laminar. We saw the nice and smooth streamlines. But if I am above, the flow is turbulent. That's a simplification of the story, because we're saying, well, there is a critical value, and below that it'll be laminar, above that it'll be turbulent. In reality, what happens is that there is a transition. And that's what I was depicting when I was just beginning to oscillate the streamlines. But that transition will occur around your critical Reynolds number. So if you're doing the experiment, and you then start writing down the values of the Reynolds number and making notes, and you say, well, Reynolds number is very small, say 0.1, and I make a note, the flow is laminar. I go to maybe 1, the flow is laminar, 10, the flow is laminar. I will reach a value that I'll say the flow is beginning to fluctuate. That always will be around that critical Reynolds number. And then if you keep going up, the flow is fully turbulent. So that's the importance of the Reynolds number. So you might ask, well, what is the value? What is the magic number of the Reynolds number that produces the transition? And what do you think the answer is? It depends on the flow, on the type of flow. It will depend on the type of flow. If it's a flow in a pipe like this, like I sketch here, if it's a flow in a pipe like that, and you control everything very carefully, you make the pipe very smooth, everything controlled, you avoid vibrations in the room, you will find that that critical Reynolds number is around 2300 for that situation. It's about 2300. When you reach 2300, you start to see the transition. But if you're looking at some other flow field, it might be something different. And that's enough for now about about the Reynolds number. We could, in fact, do a lot in this class without ever talking about the Reynolds number, but I think it is important for you to know about the Reynolds number, even though you will see a lot more of it in the second course in 130B. This means that for the most part, the flows that we're looking at this point in the course are all laminar, because we don't want to make our life too complicated yet. There's one thing about a turbulent flow having to do with one of the questions today about the steadiness versus the unsteadiness. What is a turbulent flow? Steady or unsteady? It's unsteady. You cannot have a steady turbulent flow because it's by nature unsteady. There is all these oscillations going on. So if you want to look at steady flows, you better start out looking at laminar flows because those can be steady. Now, when we study turbulent flows, there is a way to treat them as steady. Because what you say, and this is, I'm just going to tell you this so you know it. You say, okay, the flow is unsteady because it's turbulent. So what I do is I say, well, the velocity field is unsteady, is turbulent. But what I'll do is I'll break it down. I will break it down into a couple of things. I'll have a mean part of the flow. So the flow is completely unsteady, but I'll say there is a mean part to it and a fluctuation. Right? So I construct my flow field as having two parts, a mean part and a fluctuating part. And then I can look at some flows that happen to be steady on the mean. So the total flow is still unsteady. But I can divide it, I can look at it as being made up of a mean component which is steady, and then the fluctuating part which is always going to be unsteady. That's how you then begin looking at turbulent flows, because then you can, at least in some way, consider them steady. Okay, any questions about the Reynolds number? Then let's move on. The next item, which is very important for us, is the concept of the acceleration. Remember when we looked at our equation for the way we derived the Bernoulli equation? What has always been our starting point to derive those equations? No, in terms of equations. Somebody? You were answering everything last time. Newton's second law. Right? That's our starting point. So Newton's second law, of course, has the acceleration on the right-hand side. So if you think, sum of forces equals MA, when we wrote it per unit volume. So instead of MA, we had rho A, but the acceleration is there. So this is the time where we need to look carefully at what the acceleration is. So let's do that. So there is a schematic showing a path line. So this is a flow field that happens to be a path line, meaning that there is that particle there that I drew like a little black rectangle that is following its path. And I know that Newton's second law applies to such an object. This is a Lagrangian view of the fluid. I'm just looking at one particle of fluid and following it as it goes about. So of course I can take note and say, well, this particle has a velocity, which of course has to be tangent to its path. And it'll have an acceleration, because that particle is certainly not going at constant velocity. Its path may be bending, the speed may be increasing. So it has both a velocity and acceleration. So in Lagrangian mechanics, you ask yourself the question, well, if I know the velocity, how do I find the acceleration? You take the time derivative. Right? You do that in Lagrangian mechanics, then that is what you might call a piece of cake. You say, if I have the velocity as a function of time, I take the derivative, and that gives me the acceleration. And you might recall the definition of the derivative from calculus. Right? So you just take the velocity at some time later, delta t, and then subtract from it the velocity at time t, divide by delta t, take the limit when delta t goes to 0, that gives you the derivative, which is the acceleration. Okay, so you would do something like this. There is the same path line. Now I put the particle at two different places. So I drew the particle at time t, and I drew the particle at time t plus delta t. So because I want to apply my definition of the derivative. Okay? And I put a coordinate system there, x, y, z, a random coordinate system. So one thing that I note is when I draw the particle at t and then I draw it at t plus delta t, when I draw it at this second time at t plus delta t, that indirectly implies that the particle is now at some new value of x, y, and z. Okay? So at time t plus delta t, the particle is at x plus delta x, y plus delta y, and z plus delta z. Everything has changed for that particle. The time has changed and the position has changed, all three coordinates. All right. Now I say, okay, suppose that I have the Eulerian field. So now forget for a moment about the particle, and suppose that you have given to you the Eulerian description of the velocity field. That's the velocity as a function of x, y, z, and t. That means that you can go to any point in space, x, y, and z, any time, and you can find the velocity at that point. But this is Eulerian, this is not Lagrangian. But of course the velocity has to be the same, whether you look at it in the Eulerian frame or in the Lagrangian frame, whatever the particle is, the velocity has to be the same. So if I am going to compute that velocity using the Eulerian field, and I had to write that twice because the first time didn't fit. So I write the same quantity, the same definition that I have above is v at the new time minus v at the old time divided by delta t. But I'm now being careful because I'm writing it using this Eulerian field, which is v now of x, y, z, and t. So I have to do x plus delta x, comma y plus delta y, comma z plus delta z. I have that. But it's the same definition of a derivative. The difference, of course, is that now I'm looking at the velocity as a function of four variables, x, y, z, and t, with the caveat that if I want to look at the particle, right, then this x, y, and z are functions of what? Time. Right? This x, y, and z are functions of time. So it's that in this expression, it's not only that I have the velocity depending on t here, but it also indirectly depends on t through x, y, and z if I am following the particle in a Lagrangian sense. So when you take the derivative then, you end up with actually four terms. So there is my specification that the velocity indeed is a function of x, y, z, and t, but that the x, the y, and the z are functions of time. So when I do the derivative, given that I have now a v that is a function of four different independent variables, three of which indirectly depend on time, then I end up with four terms, because I do the chain rule for each. Right? So I will have dv dx, partial v partial x, times dx dt, partial v partial y times dy dt, plus partial v partial z times dz dt, plus the direct derivative on the time from the direct dependence. But I have four terms. But of course, what is dx dt? Is the velocity component. Remember, we said last time that we would write the velocity as having components in the x, y, and z directions. So it turns out that that's precisely what I have here, right? Because this one is dx dt, this one is dy dt, and this one is dw dt. So I really have there d capital V dx times u, d capital V dy times v, little v, and then partial capital V dz times little w. So that's really what I have. I just put it's a product, I just put the simplest term in front, so I put the u in front. Where?
Instead of dw, it's dz.
Here? Oh, yeah, thank you. dz dt. All right, so I have those right here. Right? So the dx dt is u, the dy dt is v, and the dz dt is w. And of course there is plus the alone term dv dt, partial v, partial t. But that's it. I have now come up with an equation for the acceleration of a fluid particle, of a fluid element. Is that, let's see what I have here. Yeah. Is that equation or that expression that has 4 terms. First time student sees this, it's a wow. I mean, this is a complicated way to compute an acceleration, especially when I compare to what I used to do in simple particle mechanics, which was just the time derivative. Well, this is the same thing. This is the time derivative. It's just because we are expressing it through the Eulerian field that it has all these terms. So, just like we did with the velocity, that we wrote it as having 3 components, we can do the same thing with the acceleration. So we say the acceleration as a vector will have 3 components. It's just we run out of letters, so we just use subscripts. So we say a sub x, a sub y, and a sub z are the components of the acceleration vector in the 3 directions. So if I go back to my original sketch here, what I have done is, well, I already have an expression for v as a vector with components u, v, and w. Now I have an expression for the acceleration with components a sub x, a sub y, and a sub z that I can get out of this big equation here. So if you break it down, because this is a vector equation, so if you now break it down into each of the components, ax, ay, az, and I don't know really if you want to write all of that down now, since you can watch it later and write it again. And if I wait until you all write it down, we're going to be here for a while. But that's it. This big red box has the 3 components of the acceleration field, a sub x, a sub y, and a sub z. And each one, of course, has 4 terms, because of the fact that the original vector equation had 4 terms. This, like I said, this can be overwhelming the first time you see it. It's certainly a long expression. And it really produces a lot of interesting things in fluid mechanics, as we will learn later on. So for now, just try to understand how the derivation comes about, and then I'm not going to ask you to memorize something like this at this point. You just need to understand where it came from and what each term means. That's the acceleration. So let me see, because this is complicated. Are there any questions about this derivation? No? Okay, so what is important to note here? Let's keep it, see if I can keep it there. And ask you something, one particular thing that is very important that you note, and is the following. Okay. There is the partial v, partial t, and there is the full dv dt. Let me ask you, what is this, let's start with this one on the right-hand side, this full dv dt. What's the name of that? That's the acceleration. That's what we just derived, right? This term on the right-hand side is the acceleration as we have just derived it. It has these three components, a sub x, a sub y, and a sub z. But it came from here. A is full dv dt, because that's a Lagrangian calculation. What is the other one? The partial v partial t. Is it the acceleration? Part of it. That's what I want to hear. It's part of it. It's part of it. Which part? Well, the one that is listed last here in this box. Right? It has three components. Partial v partial t has these three components because the vector v has three components. So this is the acceleration. That's just part of it. But that part of it is crucial. What do you think is the implication of that part of the acceleration? If we give it a name, by the way, we call it local acceleration. That's just a name. Don't let it confuse you too much. That part of acceleration we call the local acceleration. It is significant because what happens if a flow is steady? Huh? No acceleration? No local acceleration. If a flow is steady, by definition of a steady flow, which means that at a certain point, the velocity doesn't change. If I keep my eye fixed on a spot as the fluid goes by and nothing changes at that spot, that's the definition of steady, then the acceleration should not change at that point. So when this term is zero, when the local acceleration is zero, if zero, then we have steady flow. Right? And there is one thing we do to help us not to mix these two things up. Or another way to say it, to remember that this total acceleration has all those terms in there. Then to help us remember that, we kind of change the notation that we use. Whoops, we can leave that there. Okay. So what we saw as the full derivative in time, we rewrite it with a capital D. We only do that in fluid mechanics until we become extremely familiar with the fact that this is the total derivative, right, and not the local one. So to make the distinction between these two types of quantities, one that has a partial derivative in time and one that has a total derivative in time, the Lagrangian derivative in time, then we write the Lagrangian derivative with a capital D. Again, you don't do that in particle dynamics because you don't need to worry about all the components of the expressions for the derivative. And this one is given a variety of names that all mean the same thing. So I wrote there 4 names that probably covers them all. The names given to this notation. You might hear it referred to as the substantial derivative, material derivative, that's what your book calls it, the material derivative. It is the Lagrangian derivative. It's the one that we came up by using Lagrangian mechanics. And another name for it is the derivative following the fluid. So all of those names have to do with the fact that you are following a fluid particle, a material particle. But again, it's just, I, for example, myself, rarely write it like this anymore. I just go ahead and write it with a lowercase d. Has to be the straight d, though, because it has to be different from the partial. But as you read the text, you'll see how it's written in this way. So let me tell you how can we do something to write this in a more compact way. And the answer is the following. The answer is yes, and is the following. You realize now why you need to have vector calculus to take this class, because there is all this stuff that has to do with field variables. So the way to write this in a simplified way would be to define an operator in the mathematical sense. And we define that operator as velocity dot the del operator. I assume you remember what this del operator is, right? From math. The gradient operator is actually written right here. It's the second parenthesis because I have spelled it all out here. The velocity is, of course, u in I plus v in j plus w in k, and then dot the so-called gradient operator, partial x in I plus partial y in j plus partial z in k. So I just define a mathematical operator that is the dot product of these two quantities. Right? And how do you do the dot product of two vectors? Like terms, and then add them all up, right? So essentially what this gives me then, of course, is, let's think about it. It will be u times d dx, right? Plus v times d dy plus w times d dz. So it gives me precisely the terms that I have in the acceleration. So if I use that, I can write the acceleration in just one little form. Here I'm using the new notation, right? So the substantial derivative, acceleration is the substantial derivative of velocity, substantial time derivative. And here's the two parts. Now it has two parts. The one that we call local, and this one, which looks nice and simple there, but that you know it's really how many terms? How many terms are there here? Not 12. Not 3. That's a good question, right? How many? 9. Right? 9. This 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Not 12 because these 3 are here. Right? That's the local. The local acceleration has 3 terms. This other one has 9 terms. So the only thing that we haven't done is name the second part of it. We know that we call the dv dt local acceleration. The name of the other one is the convective acceleration. All right? So I'm going to leave it here because I know it was heavy and I think we are pretty much out of time. So I will see you again on Monday.